Hello again. In this video we're going to take a more analytical approach to evaluating a limit, and the approach that we're going to take in this case is a method called direct substitution. And before we get going on these examples, I need to state that there's some properties of limits that allow us to use this method we call direct substitution. And those properties, they're not hard to prove. They're not even that hard to comprehend, but there's a lot of them. And I'm not going to take the time at this point in the video to cover those different properties. So I'm going to leave that up to your calculus book or a more formal calculus class to go through the different properties that allow us to use this direct substitution technique. Okay, so here we go. This first example, it doesn't get much more basic than this right here. The direct substitution method, if you think back to all of the videos involving the graphical approach, it looked like that wherever this point was, if it was in the domain of our function, it looked like all we could do is just basically plug this right into our function, and that told us our limit. Well, sure enough, that's exactly what we can do. So the direct substitution method is exactly what it sounds like. Whatever it is we're approaching, in this case it's 2, we're going to directly substitute it into our function, evaluate it, and that should be our limit. So 2 times 2 is 4, plus 1 is 5, and we're done. Okay, so the limit of this thing as x approaches 2 is equal to 5. Now you could check that graphically on your calculator. You can even go into your table and plug in values that get really close to 2 to confirm that that limit really is 5. Okay, the second example is not as straightforward. Okay, you can see that if you try to plug -3 in for x into the function here, we first see that we get 0 in the numerator, but more importantly we get 0 in the denominator, and that's not good. Okay, so 0 over 0 is not 0. A lot of people might want to come out here and say, well, this just equals 0. Turns out that's not true. We call that indeterminate form. When 0 is divided by itself, we call that an indeterminate form. There's not a whole lot we can say about this limit if that's what we get. So we need to basically take this function and turn him into something that's equivalent that we can use direct substitution on. Okay, I like to think of this as changing the function's clothes. When you get up in the morning, you put on your set of clothes one day, and on a different day you might put on a different set. It doesn't change the person that you are, you just look different. Okay, that's exactly what we're doing to this function right here. So one thing I notice is that this numerator factors, and it factors to x plus 3 times x minus 2. Okay, and the denominator I've just left alone. Okay, now one thing you'll notice is that this factor of x plus 3 is repeated down here in the denominator. And this, I hate doing this, but I do it because everybody seems to do this, but they start canceling these factors out, and that can lead you into trouble when you just start canceling things out like that. I like to call this reducing. This is really 1, and we're just removing the special factor of 1. Okay, so really what we have left over is this new limit statement that says as x approaches -3 of this function x minus 2 that's left over, this guy effectively is the same thing as this guy. In fact, if you were to graph x minus 2, okay, I think everybody would agree that you're going to get a line. You're going to go through -2 down here, and you're going to have a slope of 1. It's going to look something like this. Okay, if you were to plug that into your calculator, you're going to get this exact same line with one exception. Out here at -3, okay, you'll notice that -3 is not in the domain of this thing, whereas -3 is in the domain of this guy. Okay, so what would the graph of this, how would this be different then? All right, well, there would just be a little tiny hole where -3 should go. Okay, but other than that hole, these graphs are identical. Okay, so really we're finding the limit of this thing right here But if we find the limit of this thing, that's effectively doing the same thing. Okay, now we can use direct substitution. Negative 3 minus 2 is negative 5. And it's no coincidence that our hole down here, our hole appears at negative 5. But since negative 3 wasn't in the domain of this function, we couldn't plug it in. Okay? So the last example is a bit more complicated, and you'll see right away that we have this square root function in here. And if we try direct substitution, we get that indeterminate form again. Okay, so the technique we're going to use here is we're still going to take this function and we're going to change its close, so to speak, so that it's equivalently the same, effectively the same, I should say, but it just looks slightly different. So I'm actually going to multiply by what we call the conjugate. Okay, this thing right here is the conjugate of this numerator. And we chose the conjugate because you're going to see that when you multiply these two binomials together that your middle term is going to drop out. Well, we better do the same thing to the denominator if we want to maintain our equivalence here. Okay, so really what I'm doing is I'm taking this and I'm multiplying by 1. This is just 1, so I'm not really changing this at all. Okay, so now if I were to multiply these two binomials together, I would get the following. I'm just going to rewrite my limit statement here. Well, my first term, when I multiply this times this, the square roots kind of undo each other and I'm left with just x plus 1. Notice my middle term is going to drop out. What I mean by my middle term is this times this plus this times that. That's just going to drop out. If you don't see that, you can draw some rainbows here that you probably learned how to do in Algebra 1. I just didn't want to make a mess of this right here. So our last term is simply going to be negative 1 times positive 1, and that's going to give me a negative 1. And down below I have x times the square root of x plus 1 plus 1. Alright, well, simplifying all this, we get the following. The limit as x goes to 0. Notice up top that we just have x now. Down below I have x times the square root of x plus 1 plus 1. And I'm not going to distribute that x through. I hope you can see why, because I have this disguised 1 right here that I can actually factor out. You might say cancel. That's fine if you learned it that way. So I'm going to rewrite this. Now, if you like the word cancel, if you want to do this, that's fine. If you cancel these guys out, you're not left with 0 up top. You're left with 1. And down below I have the square root of x plus 1 plus 1. Whoops. Okay, now you can see that we have this new function that is equivalent to this function with the exception of maybe the point 0. You see 0 is not in this domain, but 0 is in this domain right here. So we can go ahead and substitute 0 in for x right here. And we should get the following. The limit as x goes to 0. Actually, I don't want to do that. Sorry about that. Let's just do this in our head. I'm running out of space here. 0 plus 1 is 1, and the square root of 1 is 1, plus this 1 is 2. So this whole limit is going to equal 1/2. And there's your limit. Okay, so some tips for direct substitution. You can read right here the tips. I always try plugging in the value right away, and if that doesn't work, try changing the original function's close. Make it into something that's equivalent, but just looks a little different, so that you actually can use direct substitution. And always remember that you can always graph, or you can look at the table to help you confirm what your limit actually is. And if you don't know how to do that, you can go back to the previous videos to see how we evaluated a limit graphically or numerically. Thanks for your time. We'll see you in the next video.